So I work for Continuum Analytics, as Ian said. And today I would like to talk to you about a new way to send data from memory to CPU that potentially can be faster than memcpy. Maybe it's a little bit strange why I am emphasizing so much memcpy. How many of you know what memcpy means? Wow, okay, excellent. So for those of you that doesn't know what memcpy is, it's basically the system call that makes copies from one area of memory to another area, okay? So it's the fastest way, in theory, to transmit or to copy data from one part of the memory to the other one. So let's see if we can beat memcpy in doing these tasks. Okay, so a few words about me. I am the creator of tools like PyTables, which is behind the HDF store in Pandas. It's a very fast way to serialize data. Also the main author of Blosc, and also Blizz, which is a new backend for Blazor, which is an internal project of Continuum. And as Ian said, I am the current maintainer of memcpy, which is a way to compute expressions very fast. And Pandas, the latest versions of Pandas are using it too. I also learned the hard way that the premature optimization is the root of all evil. So I try very hard to not do that again. And I only hope that my last effort doing Blosc is not another example of premature optimization. So let's see. Also, some words about Continuum Analytics. We are a company that we are developing, in fact, new ways to store data and compute data and visualize data, okay? We provide open technologies for data integration on a massive scale, basically big data. And we are providing software tools, training, integration, and consulting services to corporate, government, and educational clients worldwide. So let's go to the meat of the talk. First of all, I will show you if we can compress actually faster than memcpy. I will show you some benchmarks. Then, if this is the case, how we can do that? Because in theory, nothing can be faster than a memory copy, right? And I will introduce the way due to the starving CPU problem. Then I will go a little bit in deep on how Blosc works. And I will finish by looking at it being faster than memcpy actually means that real programs with real data can go faster, okay? Because we can do a lot of benchmarks, okay? You know that there is more lies and benchmarks. But of course, if that doesn't work in real life, we don't have nothing. So we are going to see a real life example at the end. So compressing faster than memcpy. Now I am going to start an interactive session with IPython notebook, okay? So those of you that want to exercise the same thing and check by yourself if your laptops can be faster also than, Blosc can be faster than memcpy in your laptops, you can download the materials here and you can check your own. We don't have a lot of time because this is not a tutorial, but maybe later on you may want to download that, okay, and check in your own laptops. For running these notebooks, you will need the Blosc dependency and also the blz, the Blizz dependency, okay? Both are included in the conda repository, so it's just a conda install Blosc and blz away. So let's go with the notebook. I think presentation mode would be better. Yeah, I think so. Okay, so we need first to import some libraries in Python for doing our benchmark. And we are going to create an array which is 20 million large, okay? And we are going to experiment with a compression level in Blosc which is 6. It's it's a medium compression level. Compression levels in Blosc can go from 0 to 9. 0 means no compression, and 9 means maximum compression. And then n times is the number of times that we loop in order to do timings, okay? So here, we create some labels in order to produce nice plots later on. And here we are going to perform our first benchmark. We are checking here the speed of memcpy, okay? So memcpy is accessible through Python via the C types, okay? Instead of calling it memcpy, C types call it memmove, but it's the same thing, okay? So we create an array of 20 million elements made of 8 bytes integers, and also a container for getting the results, which is out, in and out, okay? And then we loop on this memcpy. So the source is here, and the destination is here, okay? And in memcpy, you need to add also the number of bytes that you are going to copy. Bytes, okay? memcpy is really low level. Okay. Unfortunately, I am using my MacBook Air, which is pretty old. Initially, I was trying to do the talk using this computer, which is much more powerful. But I had problems with the video, so I am using that. So all the numbers that you are going to see here are made in this bigger laptop. This bigger laptop is an Intel i5 with two physical processors, 2 physical cores, okay? So the time for that is 0.032 seconds. The memcpy. Then in this loop, it does apparently a lot of things. I am not going to explain everything, just that we are going to create different data distributions, okay? So we have an arrange distribution. Arrange means 0, 1, 2, 3, okay? Then the linear space, which is an evenly distributed data set between value 0 and 1,000 with 10 million elements too. And then a purely random distribution too, with values between 0 and 1,000, sorry. Then Blosc supports many different compressors. Actually, currently it supports just 4 compressors. Maybe in the future we will support more. So we loop on each of the compressors that Blosc supports, and then we do another loop for checking the time for compressing, okay? And the time also for decompressing. Here, Blosc.decompress, okay? And then we also populate different values in data frame, pandas data frame, for plotting purposes later on. So these are the results for this small benchmark, okay? These are the results for the arrange linear distribution, linear space, which is a linear distribution too, and this is the random distribution, okay? And these are the different compressors that are included in Blosc itself, okay? Here we have the times for compressing and decompressing, okay? And here we have the compression ratio. The compression ratio are really amazing. This is not a bug in the slide. This is real, okay? Blosc uses a technique which is called shuffling, that it works very well in order to compress regular distributions like this one. This shuffling doesn't work very well in case of random distribution. This is why in random distribution we don't have these high compression ratios. Okay?
Sorry, how can you compress the random ones at all?
Sorry?
Can you compress the random data 5 times?
That's a good question. So the random, okay, it only goes from 0 to 1,000. And the integers is 8-byte integers. So the highest, the most significant bytes of these integers are mainly zeros. This is why you can reach. If everything is completely random, it's impossible to compress anything, right? Okay. So here we just plot the different speeds using pandas with the data frame. We build the data frame, okay? And we are plotting for the different data distributions, we can see the different speeds. So the first bars are memcpy, okay? So this is the speed of the memcpy in my laptop. This is around 6 gigabytes per second, which is pretty typical in modern laptops. And these are the different compressors in the speed of different compressors in Blosc. So for this arranged linear distribution, we can see that Blosc LZ can be actually faster. Then there is LZ4 that can be even faster than Blosc LZ. LZ4HC, it's a high compressor mode of the same compressor than LZ4, and they share the same codec, okay? But they are meant more to spend more time compressing, and they can achieve better compression ratios. But still, the decompression ratio can be faster than memcpy, which is interesting. Blosc also has support for Snappy, which doesn't reach the performance of memcpy, and also has support for Zlib in case people prefer more compression ratios and less speed. Okay, this is supported. Of course, Zlib, it's much slower than memcpy. So this is for the arranged linear distribution. For linear space, the things are not so clear. For example, Blosc LZ doesn't reach the performance of memcpy, but LZ4, not for compression, but for decompression, can decompress data faster than a memcpy, which is an interesting thing. Even LZ4 high compression can decompress faster. It takes a lot of time to compress, but can decompress like this, very fast. Okay? So Snappy doesn't reach, but it's also very good. And then Zlib, which is meant for better compression ratios instead of speed. And here it is the random distribution. It's a pattern very similar to the other one. And we can see that the compressor that can beat actually memcpy is LZ4. Okay? In the decompression, it can go like 1 gigabyte per second faster. No, half a gigabyte per second faster. Okay? So yeah, it is possible on a variety of data distributions to beat memcpy. I encourage you to try to reproduce these results in your own laptops with the materials. Okay. So we have a couple of open questions now. First one is if compression takes way more CPU than memcpy, because memcpy is not stressing the CPU at all. Why, if compression uses more CPU, why can Blosc be faster than memcpy? This is the first question. And the second question is, this data is completely synthetic. Okay? What happens when the data is not synthetic and it's real-life data? Okay? So we need to answer these two questions. First of all, I am going to explain why Blosc can beat memcpy. So for that, I need to expose first what I what I like to call the starving CPU problem. And Richard Seitz has a nice article, which was written in 1996. I think it's worth to mention it. And in this article, Richard Seitz is one of the fathers of microprocessors and is the actual architect of the alpha processor in the 90s. Across the industry, today's chips are largely able to execute code faster than we can feed them with instructions and data. And that was said almost 20 years ago. So what happened during these 20 years? And 20 years ago, CPUs were already faster, way faster than memory. So here's the tendency between the evolution of the speed of memory in red and also the evolution in the speed of CPUs, okay? In the green line. We can see that the gap between these two speeds the gap is opening, okay, and growing. And there is no signs that this gap is going to stop increasing, okay? This blue line means the correction because around 2005, the vendors started to introduce multi-cores in processors, okay? So the blue line is the correction of the speed by adding multiple cores. Multiple cores can do more instructions in the same frequency, right? So the frequency stalled, but the effective speed continues to grow. So this is a tendency that there is no signs to stop. The problem is so evident that people is not writing small sections in books, is not writing articles, is writing entire books about the problem, okay? And this is an example which I like to cite because the title is so explicit. So it's the memory system. You can't avoid it, you can't ignore it, you can fake it. And many times we're only focused on CPU speeds, but memory speed is tremendously important nowadays. So this is the situation now in 2014. Memory latency is much slower than processors, around a factor of 100 and 250 times slower, which is a lot. That means that when a CPU asks for a data that it's not in cache, the CPU has to wait and sit and do nothing for 100 or 250 cycles. And that's a lot of waiting, okay? Memory bandwidth is different. It's improving at a better rate than latency, but it is still also slower than the processors between a factor of 30 and 100, okay? So even if memcpy is bringing data at full speed of the memory buses, the CPU could even do 30 times or 100 times more things with the data, or had to wait a lot while the data is arriving. So the main thing about Blosc is why CPUs have to be waiting for data and doing nothing. So the idea of Blosc is to do compression, okay? Instead of making the CPUs to wait. Compression and decompression. So this is the goal of Blosc. The goal of Blosc is, for example, if we have our datasets in memory here, instead of having the dataset decompressed in memory and having to transfer the dataset to the caches, why not having the dataset compressed in memory and transmit the dataset to the cache and decompress it in the cache, which is way faster, okay? And in particular, the time that it takes to transmit the compressed block into the cache and decompress it, the sum of these times can be smaller than this time. So the goal of Blosc is making these two times being less than this time, okay? And we have seen that we are going to achieve this goal.
Francesc?
Yeah?
Presumably this means that the data you're dealing with has to be smaller than whatever will fit into the cache.
Yes, exactly. The idea is that you have to store your data in blocks, in small blocks, so that you can transfer the blocks into the cache. But of course, the blocks need to fit in cache, either in L1 cache or L2 cache. Okay? Blosc is designed, the lowest compression ratios works on L1, but the bigger compression ratios works on L2 sizes, typically. Yeah. So Blosc is taking advantage of this huge memory and CPU gap, and Blosc is meant to discover redundancy in data as fast as possible. It comes, as I said before, with a series of fast compressors like Blosc LZ, LZ4, Snappy, LZ4 high compression, and Zlib. And of course, Blosc is meant for speed and not for achieving high compression ratios. High compression ratios are meant for other kinds of compressors. Blosc is all about efficiency. It uses data blocks that fits in L1 or L2 caches, as I said before. So that provides better speed, but of course less compression ratios. It's very important, it uses multi-threading by default. Nowadays, all the CPUs comes with several cores. So why you are going to have different cores without doing nothing? Okay? So multi-threading is activated by default. And then it uses the shuffle filter that I mentioned before, uses the single instruction multiple data in Intel processors, the SSE2, in all modern Intel and AMD processors nowadays. Okay? So these are the key reasons why Blosc is so efficient. Another reason is that Blosc works, as Ian was asking, by splitting the big data sets in small blocks. Okay? These blocks are transferred to the cache, compressed there, and then they are stored in what is called a Blosc container. Okay? So in theory, you can store, instead of storing your data decompressed in these original data sets, containers, you can store them in Blosc containers. So let me talk a little bit about shuffling. The filter that allows the compressor to compress much more efficiently. So the principle of shuffling is relatively easy to understand. Realize that we have, for example, 4 integers here, 1, 30, 510, and 25, okay? This is the binary and hexadecimal representation in memory, okay? Here. So what does the shuffling is that it puts the most significant bits, the less significant bits of these 4 integers together in the same area, okay? Sequentially, aligned. The second byte, they are put here in another part. The third byte here, and the last byte here. So now realize for the compressor what is much more efficient, to compress this binary stream here or this binary stream here. In this case, of course, the compressors normally tends to run faster and to get better compression ratios in this distribution. Because, for example, in this case, we have here a run of 9 bytes, which are zeros. And this is extremely efficient to compress. Okay? So this is the rationale behind shuffle. And shuffle is, as I said before, is using SS2 for maximum speed. There is one caveat, although, is that shuffling usually produces better compression ratios with numerical data, except when it doesn't do that, okay? So my advice is always check if shuffling, which is active by default, is actually decompressing, is actually giving you better compression ratios. Because if not, there is no much sense in using it, okay? We will see an example later on. This is also a demonstration of how Blosc speed is going to benefit to the advances in CPUs in the time to come. So this is the performance This is in the compression ratio, and this is the speed, okay, in megabytes per second, in a laptop which is 9 years old, okay? And here we have the memcpy speed, which was around 300 megabytes per second, but the speed of Blosc was not very good compared with memcpy. And of course, this was using only one thread. By that time, not many processors had multi-cores. This is the same plot, but using a desktop computer 2 years old. Okay? It is pretty usual, this desktop has a CPU with 6 cores, 6 physical cores, 12 threads. Okay? And this is the speed of memcpy, which is around 6 gigabytes per second. And here, this is the decompression speed. So we can see that the decompression speed using 6 cores can be like, I don't know, probably 4 times faster than memcpy. Okay? So just compare CPUs of almost 10 years ago and CPUs of 2 years ago. And this tendency is going to grow, okay? These speeds are going, the difference between memcpy and Blosc, the compression speed, is going to improve with the time. So I think we already have some hints for answering the first question, okay? The first question was, why Blosc can be faster than memcpy? Well, we have seen that Blosc data blocking optimizes the cache behavior during memory access. This is very important. It uses multi-threading and simple instruction, multiple data instructions. And if we add this to the starved CPU problem, we can now figure out why Blosc can be faster than memcpy. Okay? So this is the first answer. And then to address the second question is, how does work that in real life, okay? So let me show you an example of that. So compressions, of course, allows to store more data using the same storage capacity, but of course, it uses more CPU time to compress and decompress data. But the question is that if using more CPU means actually more wall time, okay? These are different concepts. You can use a lot of CPU, but maybe wall times are smaller, okay? And for this, we also, in the real world, we need a compressed container. This is very important. So a compressed container is meant to store data in a compressed state and transparently deliver it uncompressed to the user, or to the CPU at least. Maybe the user doesn't see the decompressed memory, the decompressed data. And that means that the user only perceives that her data set takes less memory, okay? But not only less space, but we want to know what happens with the data access speed, okay? Here it is a first example on how Blosc can accelerate things in genomics, for example, doing I/O in genomics, okay? So there is a guy who is called Mark Howison that made SIGDB, which is a format and a library to do input-output and to do queries in genomics, okay? And it happens that SIGDB is baked by Blosc, okay? So here is the speed of memcpy in red, and here is the speed in red, in black, the memcpy, and in red, the speed of SIGDB, which is baked by Blosc. So this is a first example, real data, where Blosc can actually accelerate things. Okay, this data is published in this article here. Second example, Blosc, 10 minutes. Okay, thank you. So Blosc is a command line interface and serialization format for Blosc. Okay? The author is Valentin Henel, which is sitting there. So thank you for your effort doing that. So using it is very simple. For example, realize that you have a data set on disk. So compressing it is just a matter of using the command line, using the C for compressing, and for the compressing is using a D on the compress on the compressed file. Also, Blosc allows for a very convenient way to serialize in-memory NumPy datasets. Okay? So if we have, for example, a dataset, NumPy dataset, like this one here, we can serialize it to disk by use blockpack.pack and the array file. We pass the array and the file. Okay? And then we can deserialize the file by using unpack and the array file, and then we get the deserialized data. And if we check that A and B are equals, it is. Of course, Blosc is using Blosc behind the scenes, so this happens at very high speed. Probably this is one of the fastest ways to serialize NumPy arrays nowadays. Yet another example, Blizz. So Blizz is both a format and a library that has been designed as an efficiency data container for big data. As I said before, we're using it as a backend for our nascent Blazz library. And Blosc and Blosc are at the heart of the library in order to achieve high compression, high speed compression and decompression. Okay? So I am going to skip because I am running out of time. I have 5 minutes now? Okay. So basically, Blizz is meant to store data that can be append only, not modified. It's especially addressed to this situation. And then achieve that instead of using monolithic data containers like NumPy, it uses chunked containers. Okay? So this can be enlarged pretty easily, because you don't need a copy in order to copy. You can keep the chunks, and whenever you are adding new data, we just have to compress the new data, and you get the final container very fast. And also there is a btable object in BLZ that it's the storage is columnar, so you can add new rows very easily, and the chunks are sorted by columns. Okay? Doing that by columns has a lot of advantages in many situations. I am not going to enter into the details, but for example, especially for querying, when you have tables with a large amount of columns, normally a columnar storage is more efficient. So let me show you some brief numbers. Okay. I'm not going to discuss everything because we don't have time, but you are invited to look at the notebook, which is included in the materials. Just have a look at the size of a data frame, for example, for storing, this is data, market in the stock market, the evolution of Microsoft in one single day. So that generates around half a gigabyte of information, okay, in a pandas data frame. If we are using Blizz to store it in memory, because Blizz supports both in memory and on disk storage, we can see that using several compressors, I was experimenting with different compressors and activating and deactivating shuffle But you can see that this almost half gigabyte can be reduced to 26 megabytes. This is not fake. This is real data. Okay? It happens that in general, in reality, a lot of data that comes in finance are nuns, are non-available. Okay? Because you need to align different columns, and you end with a huge number of nuns. These nuns are very easily compressible. Okay? So this is why we can reach these compression ratios here. By playing with different compressors, we can reach 20 megabytes, and even using the huge or the Zlib, okay, with highest compression ratio, we can reach 10 megabytes. That means 40 times smaller than the original data frame. That's very nice, but we want to see if that really behaves well, if we are losing a lot of speed on that. Here is the typical way to query data in Blosc, okay? So in this case, using the Zlib with the maximum compression, we're using 100 milliseconds for doing this query. And using pandas, we can get 14 milliseconds, okay? So Blosc is much slower. But Blosc, in this case, is using the slowest compressor. What happens if Blosc can use the fastest compressor? So with fastest compressor, the time goes down from 100 to 27 milliseconds. And pandas is taking 14. That means only a factor of 2. It's not that much, okay? And there is another thing, is that in Blosc, I have not been able to use multi-threading while doing the queries. So this is still a work in progress, okay? I am pretty sure if I can start using multiprocessing in this part here, we can reach very close times than pandas, for example. Okay.
Go down to 1 minute.
1 minute, okay. So here we have the second hint for open questions. Blosc usage in Blosc, for example, means not only less storage, but also almost the same time access than the data. Okay? For example, than pandas, which is very heavy for doing queries. But I still need to address these implementation details for getting better performance. So in summary, Blosc being able to transfer data faster than memcpy has, in my opinion, enormous implications on data management. Okay? Implications that we cannot ignore. It's not only well suited for saving memory, but for allowing close performance to typical and compressed data containers. And it works well not only for synthetic data, but also for real-life data sets, as I said before. You have the reference for all the projects. All the projects are open source, so you can download it, you can modify them, and you can send us, to Valentin and me, pull requests. Very, very welcomed. So I will finish with citing Richard Seitz again in this article, where finally in the article he said that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. That was said 20 years ago, okay? So the coming decade was the previous decade. And I am saying that in this decade, memory subsystem optimization will almost be the only important design issue for improving performance. But this is my opinion. Okay, so thank you very much.